Morning, everyone. I'm going to get started. I hope you can hear me okay. I hope you can see the slides okay. And we'll try and get through today's lecture online. I wanted to begin with just a reminder about test one. So test one is Thursday. It's in the regular classroom at the regular time. It has, as I've discussed before, 3 fully worked out problems on it, and it has 10 true-false questions on it. There's a review, a practice test in Canvas, and there's also the equation sheet that you'll get attached to the test in Canvas. Any questions on that? Okay, that's fine. If you want to ask questions, you can put your mic on and ask them. You could also put a question in chat, and I'll try to see it if it's in chat. It's sometimes that I miss it when it's in chat, but anyway, let's get on with if there's no questions on the test, let's get on with today's material. So in the last couple of classes, we've introduced electrical current, we've introduced electrical resistance, and we've looked at some circuits involving electrical currents and electrical resistance. We've looked at circuits involving batteries and resistors. Today's class, we're going to continue with circuits, circuits actually that involve batteries, resistors, and capacitors. And we're going to introduce what's called Kirchhoff's rules. There's a Kirchhoff current rule and there's a Kirchhoff voltage rule. So we'll look at those 2 rules for electrical circuits. And then in the second half of the class, we'll talk about circuits that involve charging and discharging capacitors that involve time-changing, time-varying currents and voltages. So that's the plan, these 2 bullets for today. So let's start with Kirchhoff's circuit rules. And I think I will start with just showing you this slide here, which is of a circuit that is an interesting circuit in the context of the last class. It's interesting because this is a circuit that actually can't be reduced to a single equivalent resistor representing the resistors in the original circuit. So we cannot reduce this circuit here involving a 1 ohm, a 2 ohm, and a 3 ohm resistor into just a single equivalent resistor and the batteries. If you look at any pair of these resistors, the 2 ohm and the 3 ohm look like they're in parallel, but they're not just in parallel with each other. There's a battery that's also in the arrangement involving these 2 resistors. Likewise, upstairs here, the 1 ohm and the 2 ohm look like they might be in parallel, but there's also a battery in the parallel arms. And so those cannot be reduced. This circuit cannot be reduced to a single equivalent resistor. We need a new way of solving this circuit, a new approach to this circuit. And that's where Kirchhoff's voltage rule, current rule, come into play. That's where we use these rules. So here's the circuit again, upstairs here. Again, a 1 ohm, 2 ohm, a 3 ohm resistor, 2 batteries over here, a 5 volt, a 4 volt battery. We've got 3 arms to the circuit. That's the way I'll refer to it. There's the top arm here, there's the middle arm here, and there's the bottom arm here. So Kirchhoff's current rule says that if you pick any location in the circuit, then the current entering that location in the circuit must equal the current leaving that location in the circuit. I.e., it says that you can't destroy current, you can't create current. If current enters a location in the circuit, it must exit that location in the circuit. So as an example, I picked this point here. I picked this point here because if you look at the diagram, I've sketched current number 1, which is in the top arm, entering that location. I pictured current number 2 entering that location, and a pictured current number 3 in the bottom arm leaving that location. So current 1 flows in, current 2 flows in, current 3 flows out. Kirchhoff's current rule says that the currents that are flowing in must equal the current that's flowing out. So I1 plus I2 equals I3, as I1 and I2 are in and I3 is out. We don't lose, we don't gain any current at this or any other location in the circuit. That's the current rule. It's as straightforward as that. Second rule is the voltage rule. The voltage rule, in the voltage rule, you think about a loop in the circuit, a complete loop in the circuit. So you walk around the circuit from some starting point until you end up again at that starting point. There are several loops in this circuit, but let's just look at this blue loop here. This is a loop where I walk along the lower arm of the circuit and then up towards the left, say, and then I walk back along the middle arm of the circuit over towards the right, and then I return along the lower arm to where I started. So that's this blue loop here. It's around this lower portion of the circuit. And the voltage rule says that the voltage changes if you add them all up as you walk around a complete loop, getting back to where you started, ending where you started, then all the voltage changes must add up to 0. So that's the voltage rule. So for example, let's imagine I start right here in the center of this lower arm, and I'm going to walk towards the left. I hope you can see my mouse. I walk towards the left, and I walk then up, and then I walk towards the right. And the first thing I meet, the first component I meet, is the 4-volt battery. And I'm going from the negative terminal to the positive terminal of the 4-volt battery. So that's an increasing 4 volts. So there's a change in potential there. So I'm going to remember that change in potential of 4 volts. I continue on walking along the central arm towards the right-hand side. And what do I meet next? Who do I meet next? I meet a 2-ohm resistor. Well, if there's current flowing through a 2-ohm resistor, there's a change in voltage across the 2-ohm resistor by Ohm's law. And so there's a change in voltage here, which is equal to, according to Ohm's law, the current that's flowing, so it's I2, times the resistance, which is 2 ohms. So 2I2 is the voltage change here. And because we're walking in the direction of the current, this is actually a decrease in the voltage, because this current flows down potential hills. And so that there's a change in voltage here. That's the first thing to know. The size of the change in voltage is 2 ohms times the current I2, so 2I2. That's the second thing to know. And then the third thing to know is because we're walking in the direction of conventional current, the flow of positive charges, this is a step down the potential hill. So it's a negative change in voltage. So we noted a minus 2I2 change in potential here. Keep on walking. I'm gonna finish my trip. I'm gonna keep on walking towards the right. I reach the end of the circuit over here on the right, and then I start heading back down the lower arm because I want to complete the loop. And as I'm walking towards the left on the lower arm, I meet another resistor. Well, that to me that's going to be another change in potential. So this change in potential in this 3-ohm resistor is going to be, again, according to Ohm's law, is going to be the current times the resistance. So it's 3I3, 3 ohms times the current I3. It's going to be also a decrease in electrical potential because, again, this current on the lower arm, I've indicated it's flowing over towards the left. I'm walking towards the left. So I'm walking down the electrical potential hill through the resistor. So this is a negative change in voltage. So we got another change in voltage here that we said is minus 3I3. If you add those 3 changes up, there was the change for the battery, 4 volts. There was a change for the 2-ohm resistor, minus 2I2. There was a change for a 3-ohm resistor, minus 3I3. they add up to 0. That's the voltage rule. And so that's the second rule that we can apply to a circuit. These two rules are really based on some fundamental physics. The first one, the current rule, is that charge is conserved. You can't destroy charge, you can't create it. That's the origin of the current rule. The second rule, the voltage rule, is based on conservation of energy. You can't destroy, you can't create energy. That's actually the origin of the voltage rule for the circuit. And so these are two very fundamental rules. You can apply them to the circuits we're going to meet in today's class. We're going to look at an example, but we could have applied them. We didn't talk about them. We could have applied them to the circuits in previous classes too. So those are the rules. I just want to say that we actually, in a way, did apply them to our work in the last class with series resistors and parallel resistors, although we just thought of them as kind of common sense rather than being more formally Kirchhoff's current and voltage rules. So if you remember this, you remember the last class, I can barely, but this was from the last class. We had two resistors in series, R1 and R2 in series, and they were connected across the terminals of a battery. And we said that in this series configuration, the current through the two resistors is the same, whereas the voltage across the pair of resistors from the battery, that's shared between R1 and R2. Those ideas about the same current through the two resistors and the sharing of the voltage across the two resistors are actually a result of Kirchhoff's rules. We thought of them as common sense, but they're a result of Kirchhoff's rules. For example, think of this point B here. The same current must be flowing in as is flowing out. That's Kirchhoff's rule. Where the current flows in through R1, the current flows out through R2, so the same current must be flowing through R1 and R2. That common sense that the same current's going through the two resistors is a consequence of Kirchhoff's current rule. The voltage sharing between the two resistors, that's actually a consequence of, which seemed like common sense, it was a consequence of the voltage rule, Kirchhoff's voltage rule. Think about walking around this circuit. If we walk through the battery, there's a potential difference. Then we walk through resistor R1. There's a second potential difference, V1. There's resistor R2. There's this third potential difference, V2. It must be that if these three different changes in potential, the one from the battery and the two from the resistors, are going to add up to 0, it must be that the potential changes across the first resistor, R1, and the potential change across the second resistor, R2, those must add up, be equal in size to the potential across the battery, equal in size and actually opposite in sense, in direction. And so that common sense that the resistors share the voltage supplied by the battery is built into Kirchhoff's voltage rule, is a result of Kirchhoff's voltage rule. The same applied to the parallel resistors that we met in the previous circuit. Again, I can barely remember it, but this was a circuit we talked about in last class. It had two resistors, R1 upstairs, R2 downstairs. They were in different arms of the circuit, and they were in parallel with this battery. We said that common sense in the last class told us that these two resistors have the same voltage across them, and it's the voltage of the battery, but they share the current that's being drawn from the battery. Some of the current goes through resistor R1 and some goes through resistor R2. This is also a result of, you can think of it as a result of Kirchhoff's current and voltage rules. For example, the voltage rule, if you go around the outer loop of the circuit, the only components in the outer loop of the circuit are the battery and resistor R1. And so the voltage across resistor R1 must be the voltage across the battery, equal in size, opposite in sense. If you went through this lower loop in the circuit involving R2, the only components in the circuit are the battery and resistor R2. So it must be that the voltage drop across the resistor is equal in size, opposite in sense, direction, to the voltage supplied by the battery. So that common sense about the voltages of the battery being applied across the two resistors and the same across the two resistors is a consequence of the voltage rule. What about the current rule? Kirchhoff's current rule. Well, think about this point over here, this node in the circuit, this point in the circuit. The current that's flowing into the battery must flow out, and it flows out through a combination of the current that's flowing through resistor R1, I call that I1, and the current through resistor R2, I call that I2. It must be that these two currents flowing out of that node, I1 plus I2, are equal to the current flowing in. And that's how the current gets shared between the two resistors. And so that common sense idea that the current is shared is a consequence of the voltage rule. There's a couple of things you have to be careful with in applying the rules, Kirchhoff's rules, the voltage rule, the current rule, and that's the signs, that's the directions of current and signs of potentials. So I've got a couple of slides here just to stress the importance of the signs. Signs crop up in applying voltage and currents rules when you cross a resistor in a circuit, because you could either go up or down in potential. And they also come up with the batteries, because you could either walk from the positive terminal to the negative terminal or vice versa for the battery. So we've got to get the signs right. The most common way that you get a circuit problem wrong using Kirchhoff's rules is by getting a sign wrong somewhere. And there's lots of signs typically. And so we've got to be really careful about the signs. So I'm going to try and stress that. So these are two cartoons, upstairs and downstairs, of me walking around a circuit. Here I am through a resistor. So this picture upstairs is me walking through a circuit from left to right through a resistor. And actually, in the lower picture, I'm also walking through a circuit through a resistor from left to right. The difference is, in the upper picture, I'm walking in the direction of the current. I'm going the same direction of the current. Both the current and I walk towards the right-hand side. In the lower picture, I'm walking opposite the direction of the current. So I'm walking towards the right, the current is flowing to the left. When I walk in the same direction as the current, then I'm actually through the resistor. I'm actually walking, it's like walking down a series of steps. I'm going down a potential hill. I'm rolling down the potential hill, because current, conventional current, flows from higher potential to lower potential. So the sign of the voltage change here would be negative IR. Conversely, if I walk opposite the direction of the current, and that's what I'm doing in the lower plot, I'm walking from the bottom of the stairs up to the top of the stairs. I'm walking up the potential hill. So in this case, where I navigate the circuit in the opposite direction to the current, then I walk through a resistor, I'm going to have a change in potential that's positive. It's going to be positive IR. So that's the signs for resistors. You can get negative IR, positive IR, depending on whether you're walking in the same or opposite direction of the current. Batteries. We also, when we walk through circuits, we'll walk through batteries, and we can walk from the positive terminal to the negative terminal or vice versa. This is a little bit more straightforward, probably. It's a little bit more obvious. In the upper picture here I am walking again from left to right through a circuit, and this time I'm crossing a battery. Downstairs here, I'm also still walking from left to right through a circuit, and I'm crossing another battery. In this case upstairs here, I walk in a direction where I go from the negative terminal of the battery, that's the short arm, to the positive terminal of the battery, that's the long arm. And that means I've increased the electrical potential is increased by an amount that's the battery's EMF. So I've gone up a potential here. So I walked out up a bunch of steps inside the battery. In the lower case, I'm walking towards the right, but I'm walking from the positive end of the battery, the positive terminal, to the negative terminal of the battery. So I'm walking down a bunch of steps inside the battery, or rolling down a hill in the battery. And so I've gone from a more positive to a more negative potential. So that's a decrease in potential of an amount that's equal to the EMF supplied by the battery. So that's the other case of science. And it's basically, if you walk from negative to positive terminal, that's an increasing potential. If you walk from positive terminal to negative terminal, that's a decreasing potential. Okay. Well, those are all the rules and some details about the rules. To really learn the rules, understand the rules, how things work, we've got to apply it to examples. So I've got an example now of Kirchhoff's rules. Let's go ahead and do that. So here's the circuit I'm going to solve. This circuit over here on the right-hand side has 3 resistors in it. 20 ohms, 5 ohms, 30 ohms from bottom to top. It has 2 batteries in it, a 10-volt battery, a 20-volt battery. It's a circuit that you can't apply our rules for equivalent resistors in series, equivalent resistors in parallel to, because there's no 2 resistors in this circuit that are either simply in series or simply in parallel. So we can't use the way we solve these problems, circuit problems in the last class, because there's no simple resistors in series, resistors in parallel. We're going to use Kirchhoff's rules. And so this is an example of Kirchhoff's rules. The problem, the specific problem that we're going to solve is to calculate the currents in each arm of the circuit. By arm, I mean, look at this circuit here. There's a top path around the circuit. That's the top arm. There's a bottom path around the circuit through the 20 ohm resistor. That's the bottom arm. And then there's a central arm of the circuit, a central path through the circuit that involves this 5 ohm resistor. So each of these is carrying a current. We don't know what those currents are. We're going to find out what those currents are. We're going to see how to do that. Okay. So the first thing I did was to think about, in applying Kirchhoff's rules, in applying the voltage law, I'm going to apply it to complete loops within the circuit. And in applying the current law, I'm going to apply it to what I would call nodes in the circuit or junctions in the circuit. So I just wanted to explore, well, for this circuit with these 3 arms, what are the nodes? What are the junctions? And I marked them here. So over here on the left is one node. It's where the 3 wires of the 3 arms of the circuit meet. And actually, there's another node, sort of mirror node, over here on the, this is the right-hand side, not, where the 3 arms of the circuit meet. So there are 2 junctions in here, and I could apply Kirchhoff's current law to those 2 junctions. There's 3 loops in the circuit. I might mark them in light blue. There's a big loop, the obvious one perhaps, that's around the outside of the circuit. So it uses the top arm, and then it uses the bottom arm to circumnavigate the circuit. But then there's also 2 other loops, if you look. There's one through the top half of the circuit, where we use the middle arm of the circuit, and there's another one that's through the bottom half of the circuit, where again we use the middle arm of the circuit. So there's 3 loops. Now, step back and think like a mathematician. We need 3 currents. We want to figure 3 currents. We want the 3 currents I1, I2, I3 that pass through the 3 resistors that I've labeled R1, R2, R3 that correspond to the 3 arms in the circuit, the top, the center, the bottom. So we've got 3 unknowns. I've just indicated 2 nodes and 3 loops. We could build 5 equations from 2 nodes and 3 loops, but we don't need to build all 5. To solve for 3 unknowns, we just need to build 3 equations. And so that's what we're going to do. We're going to build 3 equations, and specifically what I'm going to do is build one equation using the current rule by thinking one or other of these nodes. I'm only going to use the current rule once because actually both nodes give the same equation. Then I'm going to get 2 equations from these 3 loops that I've described. And I'll just pick 2 out of the 3 that provide the simplest equations. But you could pick any 2 out of 3. That would be fine too, but I'm going to pick the 2 out of 3 that you'll see yield the simplest equation. So that's my plan in going forward here. Okay, the first thing we got to do is, if we want the 3 currents, is actually the first thing you do, rather than thinking about the number of nodes and the number of loops, the next thing that you do is actually you will want to make guesses for the directions of the currents. Now, this is a really interesting thing about Kirchhoff's current rule, is that you have to start with guesses for the currents. If your guess for the direction of the current is correct, but we're guessing the direction of the current, not the size of the current. If your guess for the direction of the current is correct, then when you calculate the value of the current, you're going to get a positive number. If your guess for the direction of the current is incorrect, meaning it's going the opposite way, you'll get a negative number. You don't have to guess correct in figuring out the currents. So we could guess wrong. If we guess wrong, we get negative answers for the currents. If we guess right, we get positive answers for the current. So your guesses can be wrong or right. It doesn't matter. You'll be told at the end of the problem whether your guess that you started with was wrong or right. So look, I guessed this arrangement here, that current I3 flows into this node on the left, and currents I1 and I2 flow out of that node on the left-hand side. So that's going to be my guess of the directions. And I don't, you know, I can't remember right now whether that's actually going to be right or wrong. We'll see whether that's right or wrong, but it doesn't matter. You could guess it right, you could guess it wrong, partially right, partially wrong. It will tell you in the end from the signs of the currents whether you were right or wrong. Once you've guessed the currents, then you can answer the question of, when you walk through a battery, is it uphill in potential or downhill in potential? And we got 3 resistors here. When we walk through these 3 resistors, is it uphill or downhill in potential? Well, take resistor 1, R1. The current is flowing in the way I've labeled the directions, from the left to the right in the top arm. So the current is flowing left to right. That means that since the current flows downhill in a resistor, that the left side of the resistor is more positive, the right side of the resistor is more negative. So once I've made this guess for the direction of I1, then I know which end of the resistor is higher and lower potential. And I mark that with the plus and minus signs here. The same thing with I2. I2 is also flowing from left to right. And so I know that through the resistor, I2 flows downhill. So it must be that the left-hand side of the resistor R2 is higher potential, the right-hand side is lower potential. So I also mark that with a plus and minus sign. Downstairs here, R3. In the case of R3, we're actually going in the opposite direction through R3. So that current I3 is flowing from the right to the left. So that means that the higher potential is now on the right, the opposite of R1 and R2, and the lower potential is on the left. Again, the opposite of R1 and R2, because the current's in the opposite direction. So here's the top of the hill. I marked it with a plus for the R3 resistor. Here's the bottom of the hill. I've marked it with a minus for the R3 resistor. Okay, so that's a convention of the directions of the currents, choice of the direction of the currents, and a consequential labeling of the resistors in terms of which end of the resistors are higher or lower potentials. And I've just reproduced that figure here with the positive and minus signs with the directions of the currents on it. But I added, in addition to this point for applying Kirchhoff's current rule that we're going to think about, the 2 loops that I'm going to walk around. So one loop that I'm going to walk around is this outer loop. So I've indicated that in, what's this color here? Sort of a peach. So that's the big loop that I'm going to walk around that as one of my voltage loops. And then the other one I'm going to walk around is this small lower loop here, where I use the middle arm of the circuit and the bottom of the arm of the circuit. So that's the other loop that I'm going to walk around. So this was a choice. I actually chose that both of them involve the lower arm because I saw that the lower arm only has one circuit component in it. The other arms have two circuit components in it. So the equations will be a little bit simpler if I involve the lower arm in both the equations. But it actually doesn't matter. You could use the other loop also, and you'd still solve the problem correctly. Another choice I made in addition to the directions of the currents was actually the direction of the loops. I walked clockwise around the loops. I could have chosen to be walking counterclockwise around the loops. It doesn't matter. You can walk clockwise, counterclockwise. You'll just reverse every sign if you walk counterclockwise compared to clockwise. But the equation will actually have the same form. And so it doesn't matter whether you choose to walk clockwise or counterclockwise. I just chose clockwise. Okay. So that's the circuit. And now, finally, I get on to writing down Kirchhoff's rules, one current rule and two voltage rules for the one node in green, the two loops in peach and light blue. And here are the rules, the equations that are derived from the rules. So when I apply the current rule at the green point over here in the middle left, I've got a current I3 going in, current I1 and I2 coming out. So the currents coming out, which is the sum of I1 and I2, must be equal to the current going in, which is I3. So that's the first equation. Hope that's fine. The peach loop around the entire circuit. When you walk around the outside of the entire circuit, the only components that you meet are the 20-volt battery. I'm going to go up the potential hill in the 20-volt battery. Then you meet the resistor R1, 30 ohms. You go down the potential hill in the resistor R1 by an amount I1 R1, or 30 I1. And then when you get round to the bottom of the circuit here, you also walk through the resistor R3. It's the 20 ohm resistor. You go down by an amount in potential, according to Ohm's law, it'll be 20 ohms times I3. So 20 I3. And that's exactly what I've written down here in this. Sorry, this is the equation for the peach loop. Here's the battery, epsilon 1. That was a 20-volt change. Here's the second term, is the potential decrease when I walked across resistor R1 due to the current I1 flowing through it. Here's the potential decrease as I walk through the resistor R3 due to the current I3 flowing through it. I add all those up. Notice that one is positive, the battery, the other two are negative, the two resistors. They add up to 0. That's Kirchhoff's current rule for that outer peach loop. In this loop, this interior loop here that uses the central arm and the bottom arm, I've written down the equation for that in a similar way here. So again, when you walk around this loop, there's three components. There's the battery, there's the resistor R2 this time, and then there's R3, a resistor we met before. So when we walk through the battery number 2, we're walking from the negative terminal to the positive terminal. From the negative terminal to the positive terminal, so it's an increase in potential. When we walk through the resistor R2, we're walking from the higher potential to the lower potential. So that's a decrease in potential. It's a decrease in potential by the amount I2 R2, according to Ohm's law. And then finally, the third change in potential is when we walk through the resistor R3 again. It's exactly the same as last time we walked through it. It's a decrease in potential, again, from higher to lower potential. The amount, the size of the drop is I3 R3, or 20 R3. And so that's what I've written down here. These three changes in potential: battery number 2, resistor number 2, resistor number 3. increase in potential for battery number 2, decrease in potentials for resistor R2 and resistor R3. If you add them all up, you get 0. This is the end, in a way, of the physics part of this problem. We've now successfully written down 3 equations that relate the 3 unknown currents in the electrical circuit. And our problem now is simply to solve for the 3 unknowns, I1, I2, I3, knowing the battery EMFs, so epsilon 1, epsilon 2 are known, knowing the resistors, R1, R2, R3 are known to us. Solve these 3 equations for the 3 unknowns. So now I'm going to turn to this being a mathematical problem. Here, I know this is sort of an overwhelming amount of equations, but it's basically some basic rearranging of the equations that I tried to put all on one slide. The problem here is we got 3 equations and we got 3 unknowns. We want to solve those 3 unknowns from those 3 equations. Upstairs here, I just, like a cat, regurgitated the 3 equations from the last slide. So this is just me cut and pasting the end result of the last slide up here. The current rule and the 2 voltage rules for the 2 loops. Then I plugged in the numbers for the knowns. I plugged in the numbers for the voltages in blue. I plugged in the numbers for the resistances in black. So I plugged in 20 volts for epsilon 1 and epsilon 2. I plugged in the 3 resistances that were 30 ohms, 5 ohms, and 20 ohms. I plugged them all in. Now, I normally think of not wanting to do that. In most problems, I would not do that until I get to the end of the problem, because normally it's helpful to keep the symbols to the end of the problem because it's easier to spot mistakes, errors, keep the symbols. Because you've still got a stronger physical connection to the meaning of the equation. The exception I know for doing that is actually this type of problem with Kirchhoff's rules. It's much easier at this point to put in the numbers because it more clearly exposes, when you put in the numbers, the relationship between the unknowns, the 3 currents I1 and I2 and I3. And so I plugged in the numbers here. And then I also simplified it a bit. I saw that, look, all these numbers are multiples of 10, multiples of 5. So I can divide this equation here by 5. It'll just make it simple, sorry. It'll just make it simpler if I divide the left-hand side and the right-hand side of this equation by 5, and also divide the left-hand side and right-hand side of this equation by 5. I'll get simpler numbers. So I did that. Actually, the lower one I divided by 10. And then after doing that, dividing the middle one by 5 and the lower one by 10, I actually rearranged those equations a little bit. I rearranged the equation in the middle as an equation for I2 in terms of I3. So this equation here only has 2 of the 3 currents in. So I can write it, if I like, as an equation for I2 in terms of I3, how I2 is related to I3. So I did that. And actually, the same is true about this equation here. Because it didn't involve the middle of the arm of the circuit, it is just a relationship between I1 and I3. And so I rewrote it as a relationship between I1 and I3, how I1 is related to I3. And that's a very handy way of thinking about the middle equation as relating I2 and I3, and the bottom equation is relating I1 and I3. And so let's step down here and look at how I did that. The top equation is unchanged. That's the current rule, that if you add together I1 and I2, you're going to get I3. That's the current rule. The lower equations, now I've rewritten them. This is just basic algebra, that I2 equals 2 minus 4I3. So it's a relationship of I2 to I3, and the final equation Again, it's just a rearranging of the loop equation that contained I3 and I1. It says that I1 equals 2/3 minus 2/3 of I3. And so those are the three equations, the three new versions of the equations that I ended up with, starting with the original equations from the current and voltage law. Hope that's okay. Okay. Well, now we got the job of solving for these three equations. This is just, again, I'm a cat. I regurgitated the three equations at the bottom of the last slide. I've rewritten them here. I've given them names, equation 1, 2, and 3. And now we're going to solve for the individual currents. So how do you do this? So let me just say in words how I did it. I've written out the solutions down here. To find, the first thing I did was find what I3 is numerically. And I did that by replacing I2 in the first equation with I2 in terms of I3 from the second equation. And I also replaced I1 in the first equation in terms of I3 with this expression from the third equation. So I'm plugging in equation number 2, equation number 3 into equation number 1, ends up producing an equation that just has one variable in it. This is the magic of algebra, that is I3, and I can solve it for the numerical value of I3. And when I did that, I didn't show you all the calculation, I got 0.47 amps. You can try this out for yourself. Oh, there's a question. On the last slide, how did you get, sorry, I've got to move my screen around here to see the full question. How did I get 2/3 minus 2/3 I3, not 2/3 minus 2 I3? Let me check that. Let's go back here. Supposing I divide actually every term in here by, let's divide by 30. Let's divide by 30. This 30 here multiplying I1 will just be a 1. So we just get 1 I1. I moved it from the left-hand side to the right-hand side, so the minus I1 became a positive I1. So that's where I get the positive I1. The 20 here, I'm dividing by 30, just becomes 2/3. 20 over 30 is 2/3, and it's a positive 2/3. I kept it on the same side. Then finally, this guy here, if I divide that by 30, that's going to be 2/3 I3. It's a negative sign, and so it's minus 2/3 I3. So yeah, so you're right. I divided by 30 and rearranged for that's right. I divided by 30 rather than 10. I know why I wrote 10 because I divided by 10 first, and then I realized the smarter thing is to divide by 30. Yeah, got it. Thank you. Good point. The lesson there, right, is, when I lay out a problem on a slide, you might think, not in that case, that, I know every step exactly right. And I just go through step by step by step, solving them, knowing exactly where I'm going. That's not true. When I solve a problem, I sometimes do something and I realize shouldn't have done that. I need to go back and redo it, and do it in a different way. Or in that case, right, I first divided by 30, but then I realized I should have first divided by 10, I should have divided by 30. So solving a problem, no matter your experience, is a process of iterating towards the right answer. You might go down the wrong road. You're going to have to come back and go down the right road. And so that's an example of that. Anyway, luckily this equation is the right equation. And it did allow me, if I plug equation 2 and 3 into equation number 1, to solve for I3. Once you've done that, you've basically solved the problem. Once you got that current I3, you've basically got the current the problem solved. Because look, if you plug 0.47 amps into equation number 2, it just tells you what I2 is. It's 0.12 amps. If you plug 0.747 amps into equation number 3, it just tells you what I1 is. It comes out to be 0.35 amps. And so at that point, you've solved the equation, and we found the 3 currents. Look, this was luck on my part. Not experience, this was luck on my part. All these numbers are positive. So actually, I did guess the currents in the right direction, although that was just lucky that I guessed them in the right direction. I know that there must be at least one going in to or one coming out. So I didn't guess them all in the same, all coming out or all going in, because you know you're going to get one wrong then at least. But I happened to guess them all right. If I had guessed I3, if I put I3 to be coming out of this node rather than going into this node, this would have been a negative number, and it would tell me the current's going in the other direction. Any questions on all that? Because I've gone through Kirchhoff's rule and a long example of Kirchhoff's rule, and the goal is that we've seen the rule, understand the reasons behind the rule, and learn how to apply the rule. Applying the rule involves some physics and some mathematics, basically. In practice, when you do this, it's easy. I said it's easy to make mistakes, particularly easy to make a sign mistake. So I normally go back and check if I plug the numbers into all 3 equations, that the arc equations are literally fulfilled. So here I am, I'm plugging in all the currents into the 3 equations and checking the left-hand side equals right-hand side. That's a good check that your results are correct, because it is easy to make a sign error or some other error in Kirchhoff's rules. Here's a lecture quiz. So I'm going to submit this lecture quiz, and I'm going to give you a couple of minutes to think about it. Let's see if I'm capable of that. I'm going to publish, not submit. I mean, publish and submit, I guess, okay. So you should see now the lecture quiz published. It's a Kirchhoff's rule question, and it's a question really about this particular, if you look at this circuit here that I think I'm still sharing, this node in the circuit, it's labeled B, and it's about the relationships between the currents that are flowing, labeled here, that are flowing into and out of that arrangement. So labeled is a current IT that's flowing in, labeled is a current I1, and I24 that's flowing out. It's I1 because it flows through the resistor R1, and it's I24 because it flows through a 24-ohm resistor. That's a funny notation, but that's the notation in this figure that I stole. And so we're asked to think about those currents and write down the correct version of the current rule for those 3 currents. And so look, here's 3 versions down here, and we got to pick which one is correct. Which one of those 3 is correct? And so I'll give you another minute or so to think about that. I'll sit back, relax, have a glass of wine, and then I'll be back in a moment. Okay, let's get on with solving this and checking we've all got the correct answer to this. So what are the keys? I'm trying to use the pen here. This is going to be a struggle for me because I'm doing it with the mouse. This current is flowing in. The other 2 currents are flowing out. So this one is out. I'm not going to write out because it's completely unreadable, and the arrows on it even readable. This current is also out. So if we're going to think about the currents flowing in and out, Kirchhoff's rule, current rule, is that the amount of current that's flowing out must be equal to the amount of current that's flowing in. We're going to lose or gain no current. lose or gain no charge. So I1 plus I24 is the total current flowing out. That's the current flowing out, and I2 is the total current flowing in. So I could write the result as the current flowing in, which is I2. I'm trying to do it with the pen that I've got, but it doesn't seem to work. So I2, I'm doing it with the mouse now, so this is going to take me about 20 minutes. It's not going to be readable, but I2 is flowing in. And then the sum of the two other currents is I1. This is a bigger joke than I thought it would be, writing with this mouse, plus I24, or wish they'd used a simpler subscript, is the current flowing out. So this is a relationship. This is a relationship between the currents in and out using Kirchhoff's rule. Now I look down here and I don't see this equation. I don't see this equation, but I see an equation that is equivalent to this equation. And that equation that is equivalent to this equation, see what they've done is moved I2 to the same side of the equation as I1 and I24 and given it a minus sign. And they've put a 0 on the side that they moved the I2 away from. So that's where the 0 comes from here. And I'm looking for an equation where we got a negative I2 and positive I1s and I24. So this is the correct equation. This equation here is exactly the same as this equation here. It's just rearranged with I2 moved from one side to the other side. There's a question in chat from Ava. How do you determine that I1 and I24 are flowing out when the arrows are all pointing to the right? Yeah, let's make sure we got that. That's a very good question. This is the point that we're thinking about when we ask the question, is the current flowing in or out? We're thinking about a specific node or point in the circuit. So the arrows are referenced with respect to that point. So this arrow upstairs here is pointing away from that point B. This one is pointing away from that point B. So they're pointing out of B. This one here is pointing into B. And so that's why I chose the signs as I did and said that I2 is in, I1 and I24 is out. I hope that's okay. Right. Let's continue onwards. Let's get rid of all this stuff. And let's move on to the second topic, which is circuits involving resistors and capacitors and circuits involving charging up of resistors and capacitors. So I want to talk about charging and discharging capacitors, but first I want to say a few words about change in time in physics. So I've got a slide that is rather general about change in time in physics, and then I've got slides that are rather specific about charging, discharging capacitors, which is something that's changing in time, and so is a changing in time in physics problem. Okay. I'm also slightly stressed because I got 20 for this half of the lecture, quote half, I've got 20 minutes remaining. That's fine. I want to talk about change in physics and time in physics. There's an interesting thing that has happened over these first almost nine lectures now. I, at the very beginning of the semester, said that this course, 213, is going to be about 4 dimensions of nature. We said there was space as three-dimensional, and then there's about 5 dimensions of nature. There's space, there's 3-dimensional, there's time, and then there was charge. Now, we've seen electric fields, electric forces, electric fluxes, electric potentials that vary in space, but we've not seen them vary in time. We've looked at electrical circuits where we've had charges on capacitors, currents through circuits, but they've not changed in time. Up to now, I've taught nothing whatsoever about things changing, varying in time. We've been living in a frozen world, a frozen physics world of frozen electric forces, frozen electric fields, frozen electric fluxes, frozen electric potentials, frozen currents, and frozen circuits. Nothing's been changing. Over the rest of the course, we're going to start to introduce change into the physics we looked at. We're going to start to introduce time into the physics problems that we look at. And so this is a kind of a landmark moment. This will be our first introduction to change. And we're going to do it by looking at charging up, discharging of circuits that involve a resistor and a capacitor. So that's all to say this is going to be a big step for us. Look, here's a statement that about time that we're going to now start talking about. All of you know what time is. I know what time is. And if anybody asks us what time is, ask me what time is, I don't know how to explain. So time's a funny thing. In physics, we get kind of specific about what we mean by time, or kind of definite about what we mean by time. Time is something in physics that's measured by a clock. So it might be a clock on your phone or a clock on your wrist, but time is measured by a clock. But actually in physics, anything that changes in time, we think of as a clock. So your iPhone has a clock, my wristwatch has a clock, but actually the charging and discharging of capacitors with, are like clocks. They're like ticks of clocks. So the moral of these two bullets is that in physics, we're specific that time is something that's measured by a clock, but also that anything that changes is also a clock. So that's an interesting way of thinking about time. Let me just give you some examples of things that are clocks. Position of the sun, the earth, the moon, the planets. Those all can be used as clocks, right? They all change with time. And actually, they were the first clocks, right? Early civilizations used the position of the sun in the sky, the moon in the sky, etc., as a clock. So they're clocks. Later on, the position of a pendulum as it swings to and fro, or the position of a mass on the spring, that started to be used as a clock because they swing backwards and forwards, or the mass on the spring swings backwards and forwards in a way that's periodic and can be used as a clock. So those are examples of clocks too. But as I say, the RC circuit, whether it's a man-made one, a resistor capacitor circuit, whether it's a man-made one, or whether it's a natural one inside your brain, for example, those are clocks too. And so all these things are examples of clocks. The thing about time in physics is that time in physics enters into equations that describe, say, the position of the Earth, which we said was a clock, say the position of a pendulum, which is also, we said was a clock. And the thing about time is it's a common variable that describes the change in position of the Earth, as it also describes the change in position of a pendulum. And so you can describe things in physics that change in time with a common variable that we call time, physics time, and give the symbol t. And so this is kind of the physics times role in equations with things that are changing, like the position of the Earth, like the position of the moon, like the location of the pendulum as it swings to and fro, like the location of mass on a spring as it oscillates to and fro. And so that's a very important thing. This is quite unlike really the variable t in a physics equation. It's quite like our kind of everyday experience of time, or what we might call psychological time. So it doesn't refer to this time in a physics equation, doesn't refer to now, or doesn't refer to the present. It doesn't refer to things in the past or in the future. It's just a common variable that describes change of the Earth's position, change of the pendulum's position, change of the mass on the spring's position, change in the charge in the current in an RC circuit. Okay, let's get more concrete now and start talking about charging, discharging capacitors. They're a clock in physics. They're an example of change in physics, change with time in physics. And so we're going to look at these cases. Okay, I've got a couple of slides for charging up a capacitor, this slide and the next slide, a couple of slides for discharging a capacitor. There's quite a bit of information on these slides. I want to show you the problems related to these slides because I think the problems are better examples of the sort of things that you might meet in homework problems or in exam questions for these slides. So I'm going to show the slides to introduce the material on discharging and charging of RC circuits, but then we'll move on to solving a couple of problems. Look, this is an RC circuit upstairs here. Contains a capacitor and a resistor. That's why we call it an R for resistor, C for capacitor, an RC circuit, and a battery. Here is a switch in the circuit. And right now, the circuit is switched off because the switch is open. At time 0, I'm going to close the switch and complete the circuit. And suddenly the circuit is on. What happens? What happens is that the capacitor gets charged up by charge flowing from the battery onto the plates of the capacitor. And so if you look at these two circuits here, the difference is that the switch is open upstairs, closed downstairs. The capacitor is uncharged in the open circuit. It's getting charged up in the closed circuit. And so it's this process of charging up the capacitor through the resistor that we're interested in. Now we know that at time 0, that moment, say, before time 0, the moment we closed the switch, there was no charge on the capacitor. Uppercase Q was 0. That is the charge originally on the capacitor. We know if we wait long enough, the capacitor is going to be fully charged up. It's going to have a charge on its plates that's equal to its capacitance times the voltage supplied by the battery here. It's going to be Q equals VC, or Q equals the EMF times C. That's the basic capacitance law. So somehow between the moment we close the switch and waiting long enough for the capacitor to fully charge, the charge on the plates of the capacitor grows by current flowing around the circuit through the resistor. And our question is really, how do we get from, no charge on the plates of the capacitor to fully charged capacitor here? How do we evolve from the initial state to the final state for the capacitor? So how that's going to happen. And the next slide really says how we get there, how we get from uncharged to charged. Just a remark down here, don't worry about this too much. You solve this problem by Kirchhoff's rules. So this is actually a well-known example of Kirchhoff's rules, but I'm just going to give you, I already solved it. I'm going to give you kind of the answer to the problem. This is the answer to the problem. This is how we get from uncharged capacitor to fully charged capacitor. This is how the current flows through the resistor to fully charge up the capacitor. So look at these two graphs. The horizontal axis is time in both cases. The vertical axis is, in the upper graph, the charge on the plates of the capacitor. The lower graph is the current that's flowing through the resistor to deposit charge on the plates of the capacitor. And so we're seeing the charge on the capacitor as a function of time, the current in the resistor as a function of time. Those are the two things, the two interesting things that are in the problem. we start out with no charge on the plates of the capacitor. Initial charge is 0. We end up with a charge on the plates of the capacitor. If you look at this brown curve here, this is the evolution of the charge on the plates of the capacitor. We end up with a charge that's equal to the capacitance of the capacitor times the voltage of the battery. So we go from where we started on this last slide to where we end up on the last slide. And this is the curve that represents that switching on of the battery. And it's described, I'm going to talk about this a bit more. The time dependence is described by an exponential function with a negative exponent, but I'll come back to that. The current is needed to charge up the capacitor. Current is a flow of charge, a movement of charge. The current is actually the slope of this graph here, because it's the rate of change of the charge on the capacitor. So here's the current that's flowing through the resistor. Here's the equation for it. That current is biggest when you switch on the circuit, and it's actually equal to the EMF of the battery divided by the resistance of the resistor. That's from Ohm's law. But then as the capacitor charges up, that current starts to fall off. And when it's fully charged, there's no current anymore. And so this brown curve here is the current as a function of time. So the charge grows according to an exponential function. The current falls off after initially starting up according to an exponential function. And the exponential functions have a time scale. They have a time scale that we call tau, and that tau is the product of R and C. And so the time scale of charging up is determined by RC, the time constant. The time scale of the current flow is determined by RC, the time constant. And in that sense, this is a clock with a tick, a time constant that is RC. So if you change R and C, you'll stretch out the time constant or you'll shorten the time constant correspondingly. And so we've made a clock. We've made a clock in charging up the capacitor that has a time constant RC. And so that's the key point here. The current and the voltage don't, the charge on the capacitor doesn't arrive immediately, instantaneously. It takes some time. It takes a characteristic time. The characteristic time is the product of the resistance and the capacitance. Okay, so that's charging up a capacitor. This is the circuit for discharging a capacitor. This circuit upstairs here incorporates a fully charged capacitor and a resistor. There's no battery because the capacitor is already charged, but there is a circuit that can be completed. Right now, in the top picture, the circuit's not completed, but if I close the switch, it completes the circuit, and the charge on the place of the capacitor will neutralize itself, will discharge by a current flowing through the resistor in the bottom circuit here. So when we close the circuit, we give a path for, say, positive charge to flow off the top plate and neutralize the bottom plate. And that's what would happen, and that's discharging a circuit. This is a problem also that you can solve by Kirchhoff's voltage rules, current rules. I won't discuss it. What we're interested in, what is the result? What is the end result for, we know that we start with charge on the plates of the capacitor plus Q minus uppercase Q. We know we're going to end up with no charge on the plates of the capacitor, completely neutralized plates. How does that happen? What's the process by which this happens? And that's pictured in this overhead with these two slides. Upstairs here is the time dependence of the charge on the place of the capacitor. Downstairs here is the current flowing through the resistor as a function of time. So it's the same graphs as in the same axes as in the previous example of the charging up of the capacitor. This time, though, you see that we start with a charged capacitor. The charge on its plates is CV. That's the rule for capacitors. And it discharges with time. We see that it's discharging because there's a current flowing through the resistor that's transporting charge from one plate to the other. It's maximum the moment we close the switch, and it falls off with time. So we have an initially charged capacitor. We have finally an uncharged capacitor. It's due to some interval over which charge flows around the circuit and discharges the capacitor. The time scale of that that discharging is again determined by a time constant, tau, we call it. That time constant, tau, is again given by the product of the resistance and the capacitance. So that time constant RC also determines how quickly a circuit made of a resistor and a capacitor will discharge as well as charge. So this discharging is also like a physics clock. It has a tick of a certain length of time that's determined by RC. And so this is our understanding of discharging of capacitor. And the important point here is that the discharging is not instantaneous, and the current flow between the plates is not instantaneous. It follows an equation that has an exponential time dependence here. The exponent of the exponential is a negative exponent, and in the exponent is a time constant that we call tau, which sets the scale of the clock tick or the discharging of the capacitor through the resistor. Okay, let me show you one quick video as a illustration of this, if I can find it. Actually, I think I'm going to show you, I'll show you that at the end. We'll go to the video at the end. I want to show you a solution to a problem first, because this is the type of problem you might meet. We're told in this problem that we've got a cell, actually it's a neuron, and as you know more than I, that a neuron or a cell has a membrane with a fluid inside and outside, and there are ion channels, pores, holes through the membrane. We've in previous classes talked about the fact that that membrane can be thought of as a capacitor. It stores charge on either side of the plates, and I think we worked out the capacitance of a neuron's membrane, and it's in the example we used, it was 90 picofarads, so 90 times 10 to the minus 12 farads. We also talked about the ion channels through the from the inside to the outside of the membrane of the neuron. We talked about them as being like resistors, and we figured out the resistance of an ion channel. And there are many of these resistors or pores or holes in a membrane. There are probably 1,000 or more. And here I've written down the resistance of 1,000 pores in a membrane. And my estimate was it's 50 mega ohms, 50 times 10 to the 6 ohms of resistance. The really interesting thing is that this membrane and its pores form a RC circuit. There's the capacitance of the membrane, and there's a question, I'll answer this immediately. Will the content from this class be on the exam? The content from this exam could be on the exam. Yeah, it's all the material that is from lectures 1 through 9 will in principle be on the exam. So we've got a capacitance and a resistance that represent the capacitance of the membrane and the resistance of the pores. They form an RC circuit, and the question is here to calculate the time constant. So this is an example of a question I'm not saying I am going to ask it on the exam, but I could ask you to calculate a time constant of an RC circuit on an exam. So we're going to calculate the time constant of this RC circuit. And here's the calculation. The calculation of the time constant, the time scale of a neuron, this is basically the time scale of a neuron charging up, its action potential, or coming to rest, its resting potential, is just its resistance times its capacitance. Its resistance is 50 mega ohms, so 50 million ohms, and its capacitance is 90 picofarads, so 90 times 10 to the minus 12 farads. If you multiply this really big number in ohms, times this really small number in farads, you get a time constant. It comes out to be 0.0045 seconds. It's 4.5 milliseconds. So this is the characteristic time for activating or deactivating a neuron. And this is typical time of neurons. There are faster neurons, right? Sensory neurons and muscle neurons tend to be react faster. They have different capacitances and resistances, have different time constants. Thinking, cognitive neurons, internal neurons, they tend to have a longer time constant. So this is more of a time constant of a thinking neuron. This is a really interesting problem because it sets the time scale for how fast we can think things through, right? And neurons switch on and switch off, and that's what they're doing when we're thinking on this sort of hundredths of a second timescale. So this is the speed of thinking. Now, if you think about this, our thinking is incredibly slow compared to the switching on and off of bits in a computer. Bits in a computer can be switched on and off at gigahertz, so 1,000 million times a second, 1 billion times a second, or more. Our thinking is much, much slower. It's a million times slower. And so this is the speed of our thinking compared to the speed of a computer's thinking. Now, we have some advantages. We do a lot of things in parallel. All our sensory and muscle stuff goes on in parallel, but our thinking is actually really rather slow. That's today's class. I'll end up by sharing another screen. There's an example of charging a capacitor. So I know about overrun. If you want to stay and look at the demonstration, stay on. If you've got any questions from today's class, then additional questions, you can put it in chat, and I'll try and answer those. But let me go to the to another screen, and there's a question in chat. Will the format of the exam look like the practice test in Cambridge? Yes, it looks exactly like that. It's the same format. It's exactly the same format. 10 true-false questions should be on the practice test, and there should be 3 problems on the practice. How do you think we should study for the exam? This is what I always say, right? The exam is mostly about problem solving and some question solving. So you want to practice problem solving and question solving. There's lots of problems that we've met in class, in the lecture classes, in the recitations, in the workshops, worksheets, in the homework. I would be writing out, working through as many problems as possible. You can use those. You've met them before, of course. There's also other new problems that you can find in the textbook that are perfectly reasonable if they're on the right material. So problem solving is a key thing. I'd also look through concept questions, resolve concept questions, or look at other concept questions that are in the textbook. There's a bunch more concept questions. And so that's how I prepare. That, to me, is much better than reading the textbook. Reading the textbook, to me, is fine. It's not uninteresting, but if you like physics, but it's not so active as solving problems. Solving problems exposes what you don't know and what you do know, and forces you to solve what you don't know and learn what you don't know. And so that's the advantage of problem solving. I hope that answered the question of how to study. Another question. So the time constant is how long it takes to full charge to occur. Let me be a little bit careful about that. It's approximately the time for full charging. It's actually the time to charge, the one time constant. So 1 RC, if you look at this graph, if you wait one time constant, you are 63%. 0.63 of the way to fully charge. So it's actually a great question that I didn't mention on this plot. One time constant gets you to 63% of fully charged. One time constant also gets you to 63% of fully discharged. If you weighted 2 time constants, so that would be about here on this slide, I don't know the number exactly, but you would be 90-something% to being fully charged. You're still not quite fully charged, but you're very close to it. So the time constant is a measure of the time to get charged, but it's not the time at which you're fully charged. That would be you'd have to wait several time constants. I can show you that actually as a demonstration. So let me change the slide, because here you'll see the time constant in action. I'm going to stop sharing that screen and I'm going to reshare something else. And I'm going to share this little video. So in this video, you'll see me, this is a capacitor over here on the left-hand side. This is the right-hand side, thank you. Over here on the left is a battery, and upstairs here is a resistor. It's a light, so we can see the power dissipated in the resistor. There's a complicated switch that if you throw the switch to the left, I won't go through all the wires in the circuit, but if you throw the switch to the left, it connects the resistor, the capacitor to the battery and will charge it up. If you throw the switch to the right, we'll connect the capacitor to the resistor and we'll watch it discharge. And so that's what we're going to see happen here over the next minute. Actually, I am going to point out I'm going to show you the charging circuit where the battery is connected to the capacitor. I'm charging up the capacitor. Now, great, you can't see the charge accumulating on the capacitor, but I did accumulate charge on the capacitor. Now I'm going to show you that I did accumulate it because I'm going to connect the place on the capacitor together through the resistor, the light bulb. So I'm going to discharge. Look, you can see the current flowing off the place of the capacitor through the light bulb, through the resistor here. And you see the time constant. You see that bulb was really bright to begin with, and then is falling off with time. We're literally seeing the time constant, that an RC circuit is a clock. It has a characteristic time. If I replay this again, it's dying out now. It's still a little bit of charge, still a little bit of current flowing in the circuit. Maybe we've reached 2 or 3 time constants there. If I go back to flipping that switch to discharge the capacitor, let's just watch it one more time because I love watching this one. There's a momentary burst of current and then it starts to slowly shrink away. It's taking a few seconds, few more seconds, and we're seeing the light bulb decrease in intensity. We're seeing the current flow off. Maybe that's one time constant. That was about 10 seconds perhaps. Now we're watching the light bulb go less and less current flowing, less and less charge on the capacitor. Maybe this is 2 time constants, and so on. And by the end of the video, maybe we don't see the light bulb at all. It's vanished to almost nothing. That's probably 3 or more time constants. That's a longer answer to that question than you probably wanted. Any more questions? Will we be given the equation sheet during the exam or are responsible for bringing it? Now, I did announce this before, but it's important that don't bring an equation sheet or a copy of the equation sheet. It's the last 3 pages of the exam. So you have to use the equation sheet that's attached to the exam, not to bring a copy of that or some other equation sheet. So that's a very good point. Thank you. Well, I'll hang out here for another 5 minutes in case some questions come up, and I can answer any questions from the. Okay, yeah. How long will we have for the exam? It's a 1-hour exam. You have 1 hour for the exam for the 3 problems and the true false. So that's the time, and so that fits easily in our class, which is 1 hour and 15 minutes. So we'll run. You know, if we were literally to start at 9:30, the exam would be over at 9:30-ish, at 10:30-ish. Bye. Okay. So if there's no more questions, I'll be getting off in a moment. But firstly, thanks for joining in on the Zoom call. It was like COVID old days again. I know that Zoom is not the best avenue for sitting through it, an hour and 15 minutes of lecture, especially as I went over time. So thanks again for joining in, and I'll see you on Thursday. If you've got any questions about the test that come up, you can email me, you can make an appointment to see me. I don't think, yeah, you'll have to just see if you want to meet with me, and let's just make an appointment, because I don't have official office hours until Thursday. Thanks, and bye.